Numbers are everywhere, and there are different kinds of them. Some are small, some are incredibly big. Some are whole, some fractions, and some even go on forever without repeating. But no matter how different they all seem, they all share something in common. They feel real. You can count them, measure things with them, and use them to describe almost anything in the world around you. From the distance between planets to the time it takes to blink, numbers help us make sense of reality. But here's the strange part. As complete as numbers seem, there are moments when they don't quite behave the way we expect. Situations where the numbers we rely on start to feel limited, like something crucial is missing. And for a long time, mathematicians believed everything could be explained using the numbers they already had, that every problem had an answer somewhere on the number line. But then a question appeared that didn't seem to belong, a problem that couldn't be solved using any number that actually existed. And it all began when mathematicians tried to find the square root of a negative number. What is the square root of a negative number? Before we get to the answer, let's ask ourselves what exactly is a square root? Well, take any number. Let's take 4, for example. The square root of 4 is just asking what number multiplied by itself gives you 4. And the answer is 2, because 2 times 2 equals 4. Notice something here. We're not doing any complex calculations or using any advanced formulas. We're actually just answering a simple question. What number multiplied by itself gives us 4 back? And that number is 2. Let's try another one. Let's take 9. Again, we ask ourselves, what number multiplied by itself gives you 9? And the answer is 3, because 3 times 3 is 9. Simple, right? Now, let's take a different kind of number. Let's take a fraction, a really, really small one at that. Let's take 0.25. Now, 0.25 is a really small decimal number, but the question is still the same. What number multiplied by itself gives you 0.25? Putting 0.25 inside the square root, we get 0.5, as 0.5 multiplied by itself gives us 0.25. So even small numbers have square roots. And this tells us something powerful. It doesn't matter if a number is big, small, whole, or even a fraction. We can always ask the same question and we always get a definitive answer. It seems to always work. No matter what number you pick, there is always some number that, when multiplied by itself, gives you the original number. But now let's put in something very different and let's try doing what ancient mathematicians did. Let's go all the way to the left on number line, past the 0, and we arrive in the realm of negative numbers. And let's try the first negative number, which is -1. Again, we ask ourselves, what number multiplied by itself gives you -1? And let's try answering that with what we already know. If we take 1, then 1 times 1 is 1. So that doesn't work. If we take -1, then -1 times -1 is still a positive 1. So that doesn't work either. And this is where we seem to have hit a wall. No matter what real number we try, positive or negative, when we multiply it by itself, it always becomes positive. Always. So, how can we ever get a negative result? It feels like we've hit a wall, a point where math just stops working. And for a long time, that's exactly what people believed. They thought there is no answer. But instead of stopping, mathematicians asked a different question. What if the problem isn't the number? What if the problem is the system? But if our number system is simply incomplete? So instead of giving up, they did something bold. They created a new number, a number defined by a single rule, a number that, when multiplied by itself, gives you -1. And they called it I, iota. And what is I? I is simply the square root of -1. And I multiplied with itself gives us what we want, -1. Now, this might feel like cheating, like we just made something up, but we have done this before. In fact, math wouldn't even exist without such made up things. Negative numbers didn't always exist. Fractions didn't always exist. Even zero was once a strange idea, and yet all of them are essential now. So we just accept a new rule, like we accept that zero represents nothing. And suddenly, that impossible problem, the problem that troubled mathematicians for centuries, has an answer. And it doesn't stop there. With our new rule, we can find the square root to every negative number. Let's try -4. While putting -4 inside the square root, we can write it as the square root of 4 times the square root of -1. We already know the square root of 4 is 2, and the square root of -1 is I. And there we have our answer. The square root of -4 is 2i, or 2 iota, because 2 times 2 is 4, and I times itself is -1. Putting it together, we get -4 as the answer. And just like that, negative square roots start making sense. So instead of trying to fix the problem or ignore it, we just expand the system. And this is the key idea. Math doesn't break, it grows. And this I, being the square root of -1, is exactly what is imaginary about imaginary numbers. And they're not imaginary because they are useless. They're called imaginary because we can't see them on the number line we are used to. Think about it. All the numbers we have used so far, positive, negative, fractions even, they all live on a straight line. You can point to them, you can place them somewhere, but where would you put I? It's not positive, it's not negative. It doesn't fit anywhere on that line. So instead of forcing it to fit, we do something new. But imaginary numbers, do they really mean anything? Or do they just exist on paper? Turns out, imaginary numbers do some very real things. Like, for example, in electrical engineering, when we are dealing with alternating current, we see that electricity just doesn't flow in one direction. It oscillates, it moves back and forth. And to describe that motion, real numbers alone aren't enough. But imaginary numbers handle it perfectly. In physics, when we talk about waves, light, sound, even the behavior of particles, we use imaginary numbers to capture patterns that real numbers can't fully express. In signal processing, when your phone plays music, streams a video, or sends data, it breaks signals into frequencies. And at the heart of that process are imaginary numbers. In quantum mechanics, the equations that describe reality at its smallest scale depend on I. Something that once seemed completely impossible, something that shouldn't even exist, is actually a very real part of the modern world. And that changes the way we see them. They're not imaginary, they're just not visible in the way we expect. And that is the very real story of imaginary numbers.